Now I want to discuss fracture things. The title you can see, fracture propagation during fluid injection. I will discuss one experiment, one modeling effort, and one monitoring technique that we have used during our last India-Norway project. So let me go to next page. This is the outline. So I will give some scenario, some example of fluid injections at field scale, and then I'll discuss what problems are the operators facing during fluid injection, and what are the explanation and research targets to solve those issues. Then we discuss experiments at our lab and how we analyze those data, what we get out of it. And then we try to develop a discrete element model to simulate the fluid injection situation and to find out the important parameters from our simulation. And my final topic would be the monitoring technique. We developed a new monitoring technique, and we think, or we have also checked that it's doing a good job compared to the old technique what is available now. And finally there would be some conclusions. So here is one example, oil and gas production in the field. In the left side you can see that there is a injection well and a production well at the right. So to extract petroleum, oil or gas, you have to inject some fluid in injection well, and then through that building the pressure and pushing the petroleum or the oil inside the rocks, you can actually produce that through other production well. In the right hand side you can see another example, the example of shale gas extraction. There we need to create some fractures. It's called hydraulic fracturing. Normally people pump some fluid like water or mixed with some chemicals sometimes with a very high injection pressure, and that pressure creates some fractures. Those are the channels to extract gas from the tight reservoirs. Another example is underground CO2 storage. We need to inject CO2 inside the porous rocks, and it should be a permanent storage, I mean the long-term storage. So we need a very good candidate for that. I mean, by candidate I mean the storage place. There are some criteria that has to be fulfilled, and it could be underground in the land, or could be below the seabed also sometimes. The final example is geothermal energy production. The basic principle is that we inject cold water and we should get back hot water or steam, because we are pumping in a layer where there are rocks with high temperature. So the cold water should go through those area, and then we will get back hot water or steam that can be used to generate some electricity. But you can see that we need to create a very nice channel, flow channel inside the rock. And for that purpose, we need to create fractures. So these are some application areas in the field where we use fractures, and definitely we want to create fractures. So we need to control it. Now I'm going to present some problems in field cases that the operators often face these problems, that sometimes the water you have injected is directly coming out from production well. So you are not getting any benefit. You are pumping water and getting back water. So you should get oil or petroleum in your production oil, but sometimes you are getting the injection water. So the problem is that maybe there is a fractures which is connecting your injection oil and your production oil somehow. So the water is not displacing the petroleum, rather it's coming directly to the production oil. During the drilling, another problem arises is called mud losses. You know that during drilling, we have to use some type of mud. And if during drilling some fractures open up, then mud goes into it, inside that fractures, and you get mud loss. So muds are costly, and if you face this situation, then you cannot actually go with your drilling plan. You have to change. Sometimes you lose your oil. And if that fractures is quite big, it can result like a borehole collapse. It's a total collapse of the borehole. So sometimes it happens. And few years back, one scientist came from Canada to our department, and he was discussing that the numbers of gas wells in Canada are leaking. So it's really an environmental issue there. And in US, one group of researchers, they reported another problem, that a lot of activities, microseismic activities, have been recorded far from the injection well. They were working with the CO2 storage project. So they injected CO2 in one area, but they observed a lot of activities far from that injection point. So they are trying to understand what happened actually, what went wrong, or is there some connections between the injection well and the area where they are having a lot of microseismic activities. And the final point I want to mention, that sometimes this field permeability it seems that it is much higher, 10 times or more, 100 times sometimes, than what people estimate through the lab test or theory. So when you have a estimate of permeability, you plan your drilling or production accordingly. But at field, if you see that it's much higher than your predicted values, then it creates a lot of problem. You have to change your planning completely. So what would be the solution or explanation of the problems I just presented? So it linked to fracture things, that how and when fracture opens up. Is the fracture pattern different for different type of rocks, types, and field conditions? And how important is porosity level? If there are pre-existing fractures in your field, then how do you plan your fracturing, your drilling or production things? How can you characterize a fracture network inside the rock or inside your field? Can you calculate the fracture propagation velocity? And related to the gas leakage, can you assess the leakage possibility if you know the pattern of the fracture or fracture networks inside your field. And finally, how can you monitor fracture propagation? If you want to create fractures, then you need to know that how they are actually propagating and how far they can go. Without that knowledge, you cannot use it in your purpose. So now I come to one experiment that we did few years back in our lab. So we wanted to create the field-like situation that we have a sample and we drilled one hole and we pumped some oil through a tube to create the borehole pressure. And we just increase the pressure until we get fractures. So the left side you can see the planning for our experiment, the sample inside, and there are 4 pressure channels, and there are acoustic transducers that can record the cracking events inside the sample. So in the right hand side top, you can see a cross section of our sample and the placing of the acoustic emission sensors, the sleeves, and the position of the borehole. And at the right side below, you can see the plan for our pressure, how we increase our borehole pressure. So there are few pressure parameters, like one confining stress, one borehole stress, and we measured pore displacement and radial deformation through our measuring system. It was performed in a TerraTech load cell. So during the experiment, we recorded acoustic emission events. All the green dots are acoustic emission events. And as you can see, this red line is how we increase the pressure. And the black line is the confining pressure. We kept it mostly constant. So these are the acoustic emission events, that means the crack openings. And as you can see at the final stage, when there is a drop in the red curve, drop means a fracture opened up and it just connects the borehole to the confining area. So there is a sharp drop of the stress, and there you can see a lot of acoustic events, and they are high in amplitude and quite dense. So the main fracturing is happening where the red curve shows a sharp drop. So through the system we used, it's called Valen acoustic emission recorder. You can locate the acoustic events, and in the left I have shown one panel of this acoustic recorder. The numbers are the position of acoustic transducers, and all the green dots are the acoustic emission events having magnitude or amplitude more than 60 decibel. And the right side is the original sample we used after the test. We have taken this snap, and you can see a clear fracture line. And if you compare with the panel in the left hand side, which we have gotten from the acoustic emission system, that there is a good match, that the density of all acoustic events, the big events, are appearing around the major fracture line. We can do some more analysis on these acoustic emission events, that what is happening at the failure point and failure time. If you just plot the time, this red curve is again the pressure. So pressure drops at the fracturing point, And if you plot all the acoustic events before this fracture point and after this fracture point, you can then plot them in the space to see that where they are appearing actually. So from the right, the picture at the right, you can see that after the fracturing point, all the blue points, they are mostly appearing on the fracture line of the fracture. But before that, all the yellow points, they are actually almost everywhere. So they are appearing before the onset of this main fracture. So we did another thing that after the test, we sent all our samples for this microcity image analysis. Actually, we did the analysis, but we got the image from one company who are doing this microcity scanning. So I have given here 4 examples of 4 different type of rocks. The first one left side is Beria, and then Castlegate, the Wildmoor, and Mons. Mons is a chalk type of rock, and the other 3 is a sandstone. So you can see that in sandstone you have a very clear fracture plane. I think it's not that visible in your in the slides there, but it is really very nicely visible. But for sandstone it's very clear, but for chalk there is nothing like a clear fracture plane. The fractures are everywhere, and this is expected because chalk samples are very, very brittle, and then you can't expect a very clear fracture plane there. We used another commercial software called Avijo for this image analysis. It gives us better insight of the sample. Here I have given 2 examples. One is a red sandstone called Mount Simon sandstone, and from the image we have reconstructed the fracture network inside the sample. So the first picture is the real sample, and the second was the reconstructed microcity image. So you can see a fracture plane like a shear plane, and also there are weak layers inside the sample. That also we can capture through this image reconstruction. And the right hand side, there is a normal sandstone called Castlegate, and here there are we can't see any weak fracture planes, only a shear fracture. Now I come to the modeling part. So we know that we are injecting fluid with a high pressure at the central point at the borehole, and that can create fractures, and that fracture propagates inside the sample. So we have tried a discrete element modeling, and we used this idea of invasion percolation and distance dependent K. K means the stress intensity factor. So our inputs are tensile strength. So each and every point in this discrete element modeling have a certain strength. So if this stress intensity factor is bigger than that strength, so we remove that that element from the model, so that creates a fracture or a crack there. So there are breaking criteria, there are porosity, and we have sample size and borehole pressure as an external parameter. So here are 2 examples, one with porosity 0. So if we don't allow any initial porosity, just a compact rock, and we run our simulation, we can see that the fracture opens up and there are 2 branches, one main branch going to one direction and another branch to the opposite direction. So these things we have seen in the real laboratory experiments, that whenever some fracture is opening in one side, there is something is happening just at the opposite side of the borehole. And when we take porosity 30%, the right hand side, you can see the fractures are a bit more rough, and maybe because of this porosity it's easy to bend, or that's why the roughness is bigger than the compact model. If we choose a, yes.
Yeah, why the fracture is so rough when the porosity is 0? I thought that we would just strip it like one straight crack.
No, because of the distribution of your tensile strength, we are not considering a single strength for all the elements. There is a distribution of strength. That's why it's rough. But you are right. If you take all the elements to be of same strength, then you can expect a single line. Yeah. Here is a less brittle rock. Less brittle means we introduce this strength and make it wide. So this distribution is big here. That's why we call it less brittle. And for one example for porosity 0 and another for porosity 30% again. So it's much rougher than the brittle model. The third case, if you have a pre-existing fracture inside your sample or inside the field, how your new fractures is interacting with your pre-existing fracture. That's an important problem, and people are trying hard how to understand or how to plan it properly, because when you are planning a drilling in a rock where originally there are some fractures, whether you can avoid them or you can use them in a good way to increase your productivity, but at the same time for stability purpose you always want to avoid fractures, right? So the first example with one fracture, you can see that the new fracture at some point it touches the pre-existing fracture, and then it percolates completely to the end of that fractures. The similar thing happens for the second case, where we have 5 pre-existing fractures. So when your new fractures touches the left side big fractures, it just percolates to the end and quickly it touches the boundary of the sample. So this is the discrete element modeling is not, we have just started it, so it's not mature enough, I would say. There are a lot of things we can study, like the properties of fracture path, the roughness, fractal dimension, we can measure the effect of sample size, hole size, and effect of pre-existing fractures. We can include temperature effect, mineralogy, and fracture pattern. If there are anisotropy in your stress situations, so how that can affect your fracture propagation. It's an interesting problem. And definitely the fracture propagation velocity. It's very important to know how far and how quickly your fracture can propagate. And we definitely should do the 3D modeling if we want to compare the scenario with the real case or the field case. The final thing I was thinking to just touch is that acoustic monitoring, how we can improve the event location. You know, This is one example. The red line is the red dot. This is the estimate from the Valen system we are using. And the green dot is the corrected location of an AE event when we used our improved anisotropic model. I'll just explain it in the next time. So what is the basic problem? That you have, as shown in the figure, you have these red dots are the location of acoustic emission transducers. They can catch the signal when there are crack opening. And then what they record is the time difference. I mean, the time, from the time you can take the time difference. So if you have 5 times, you can get 4 time differences. And you have to solve these time differences to get your target location. And for this purpose, the software we used in our Valen system is, it's given by the company from where we bought the system, and they use only one velocity. It's called isotropic velocity model. So in all directions, the wave is propagating with exactly same velocity. And we thought this is a oversimplification. I mean, whenever you have fractures in the line of propagation, you would expect a different velocity. So that's why we make this anisotropic velocity model. So our inputs are location of sensors, the arrival time records, and the third thing, the velocity matrix from pulsing table. So if you don't know what is pulsing table, that from these acoustic transducers, they have a pulsing mode. That before the experiment, you can start this mode so that one transducer sends a signal and all the others, they can receive that signal. So from there, you can make a velocity matrix that will give you the velocity values in different directions. So by this, we can make a velocity matrix with different direction cosines, this alpha, beta, and gamma. And next time, when you do your real experiments and you observe all these time differences, you can use this velocity matrix to optimize the location of your acoustic emission source. So we have used this model and we saw more than 10 times better result. I mean, in terms of the location, the XYZ coordinates, we are getting much more, I mean, accurate result than the isotropic velocity model. Now I come to the conclusion. So it's first few points are just the summary of what we discussed today. That fluid injection can trigger rock fracturing, and induced fracture can also deactivate existing fractures or pre-existing fractures. So we need better understanding of the dynamics, how fracture propagates through disordered systems. And fractures are really fatal for borehole stability because they can create the borehole collapse situation. And for enhanced oil recovery or gas recovery, we need fractures to increase the permeability, but it has to be done through a controlled way, because you cannot afford to damage your borehole or your the whole field. And fractures are really a safety issue for CO2 storage and gas production wells, because some of them are leaking. So how to tackle with that? There is some ongoing research, and but at the same time, if we can create fractures in a controlled way, the CO2 storage could be much quicker. I mean, the absorption rate can be increased by creating more absorption surfaces through creating new fractures. And for geothermal energy production, we need to create better channels. So better flow channels are essential for geothermal energy production, and again we need to control our fracture propagation, and we need to create a very good fracture networks. So finally, the research challenge is how to characterize fractures inside rocks or inside the field, and how to monitor them through active or passive monitoring. The acoustic emission monitoring I discussed a little while ago. It is definitely a passive monitoring, but there are some active monitorings from the log data. When you are doing some operation, from the log you can actually get some information of temperature, pressure, and some other stuff. So from there you can have some idea of your fracture tip also. So this is what I plan to discuss today. And I'm now working as a researcher in the PORE lab, the new Center of Excellence, owned by the physics department, NTNU. So you can have a look at porelab.no, and there you can see all our ongoing activities, our projects, and yes, if you have some questions and comments, I'll be happy to answer. Yes, sir.
When you are increasing the injection pressure, you are
yes.
doing it continuously. Now, at any level of pressure, you can increase the amount of pressure by a small amount, fixed amount, and
yes.
Get the response in terms of, in terms of the acoustic emission. Can you
yes.
find a kind of breaking susceptibility so that when your pressure is actually going to the breaking point before when it goes down, you cannot retain any pressure. Before that, is there a kind of susceptibility, the kind of thing that you have also studied earlier, theoretically? Do you have a kind of breaking susceptibility from your acoustic pressure that increase is actually, at every stage of pressure, you can increase a little bit, which is by a fixed amount, that's the D of pressure, dP, and you get the emission result, and then you say that that's a kind of susceptibility. Is there a susceptibility diverging kind of thing before the final fracture?
Sir, I can't hear you properly, sir.
Okay.
Yeah. You are discussing. You are asking about the increase of injection pressure.
Increase of injection pressure at any level of pressure, you increase a little bit more. With a fixed amount, and then there is an further increase in the acoustic activity.
Yes. Yes.
And from that you can find out how much energy has been kind of released, and you make the derivative. The thing is d of the energy released by dP. This extra injection pressure. This susceptibility kind of thing, does it grow very much and clearly that you can have an inverse power of that, so that it goes to a pressure, you can predict the pressure where it will break finally.
Yes, I have not mentioned it, but we also can record the energy of these acoustic events, and also the rate of events. So this rate of events is actually diverging near the fracturing point. So that can be treated as a susceptibility.
Yeah. Could you find an inverse susceptibility exponent so that your pressure point could be actually a straight line, and you could say that this value of the pressure, it will finally fracture will occur, and you really observe that.
Okay, that I think that we have not looked at, but we can.
Breaking susceptibility exponent.
So from this energy.
And the inverse power of the susceptibility, 1 upon that exponent, is actually giving a straight line with respect to pressure, and that susceptibility is diverging. That means
at the fracturing point
actually going to zero at a particular point, which can be straight away kind of extrapolated, and you can see that this is the pressure where actually it broke.
Yes, I agree with you. We will check that from the data. Okay. Yeah, thank you.
I just have a couple of questions.
Yeah.
Exactly on the something that I think would be very interesting to know is if you could study the distribution of energies, but as a function of a window that moves towards the table.
Yeah.
It's important to know whether this distribution of energy has a fat tail, whether it's a power law distribution, and whether if it's a power law, whether the exponent is changing when approaching the final point. Because this has been studied in other conditions, and my feeling is that this will depend on the kind of rock you have. You thought that you are studying some rocks which are more
brittle. Yeah.
And you could deduce a similar question just by measuring not the distribution, but simply the average energy.
Yeah.
The average energy in the brittle rocks probably should be constant, and the increase is only on the activity.
Yeah.
Whereas in the more or less brittle rocks, you can have an increase of both activity and average energy. So and this also will mean that the exponent is then changing.
Yeah. Okay. Thank you for this nice question. We have actually measured that, and we have seen that this exponent is actually changing as you are going close to the fracture point, because the exponent of the distribution.
Increasing or decreasing?
Yeah, exponent is decreasing, I said. Exponent
less negative.
Yeah.
Okay.
But I have not shown this result here, so but it's decreasing. We have measured.
Events,
yeah. There are more bigger events as you go close to the fracture point.
Yeah, but this occurs for which kind of rocks? The brittle or the other one?
This is for brittle type of rocks.
For brittle?
Yeah. I think as you see, we have used only Castlegate or sandstone and only chalk. So to us, chalk is more brittle than Castlegate. But this change of the exponent, we observed it clearly for sandstones, but for chalks it's not very convincing because of their breaking pattern. Yeah, that's what I'm saying.
Yeah. Then I have some other technical questions. What system are you using? Is this Mistras or it's a Valen?
Valen acoustic system, Valen. V-A-L-L-E-N, Valen.
Okay. I wanted to know something. I am using a Mistras. I also work in acoustic emission. I am using a Mistras system. But my experience is that what you obtain from this table of when you excite with the transducers and the times you obtain and you generate this table of times of travel from one transducer to the other, my experience is that this information is really not very adequate for the location of the events because the source, the generation of the event when there is a fracture, this has a frequency distribution that I think is rather different from what you can do exciting with the transducers. And then the way the waves they attenuate can be very different. So the kind of corrections that you are trying to include, I'm not sure they will be the correct ones. Do you understand what I mean? It's not the same to excite with a transducer than to produce a fracture.
Yeah, I understand your concern. Yes, that's true. That's true, but with this apparatus, if what we wanted to improve is that the inbuilt software is using only one velocity, isotropic velocity model. So we wanted to put this velocity matrix, what we can get from the direct measurement on different type of sample. So we wanted to see how that can improve our location. But I agree with you that this attenuation and all these factors, if you really want to pinpoint your location, you have to consider those things. Yes.
Thank you. Okay. Any more questions? You have to come here. Can you hear Srutarshi?
Yes. No, I can't hear you. but I'm sorry to say that I have to run for to another meeting. It has started at 1 o'clock. But yeah, it is the last question I can take. Yes, sorry.
So my doubt was that because you were showing some plots where for different porosity, there
Yeah.
are different patterns of the cracks. So
Yeah.
so once I was wondering whether should it be possible to have a direct relationship between the crack propagation velocity and the porosity?
Yeah, it could be. I mean, it depends. I mean, you know that porosity means if you make it more porous, then fracture can propagate faster,
Yes.
right?
And
So, yeah, that
yes. And should there be any universality kind of relationship?
yeah that we have yes there could be, but we have not investigated yet. That's what I meant, that we just started this one, and there are a lot of parameters we should study one by one.
Okay, thank you.
Yeah, thank you.
Okay,
Yes.
Srutarshi, thanks very much.
Yeah, thank you.